Alright, welcome to another AQA A-level chemistry video. Today I'm going to make a video on free energy. This is essentially a continuation really of the last video where I was talking about entropy. Now, if you remember from that video, well, first of all, free energy is relating to enthalpy change, entropy, and temperature, as I'll go through. Now, but in the last video that I talked about entropy and how if you increase the entropy, the reaction is more likely to happen because you have more disorder. When there's more disorder, the particles have a higher probability of reaction because there's more combinations, there are more possibilities for the particles to react when you have more disorder. When there's less disorder, there's less different possibilities and different ways the compounds can react. So therefore, the reactions are usually perceived as being unlikely to happen. Now, in essence, what I've tried to say there is that increasing entropy generally means that the reaction is more likely to happen. But as you can hear from the tone of my voice, that isn't technically 100% true all the time. And I said it in that video, there's an equation that relates and explains why that isn't 100% true all the time. And that equation is something I'm going to go through today. But there are instances where you can have a very high entropy, but the reaction is still not feasible. And I'm going to go and explain what I mean by that in this video here. There's an equation that you need to know, and that's the Gibbs free energy. There are calculations associated with the Gibbs free energy, which is just once you know the equation, it's just about rearranging the equation because they may ask for different things like the enthalpy change, the temperature, and the entropy change, and they'll give you everything else. But all you need to do is just rearrange the equation. But that's not going to be difficult. But it's about understanding what the equation means, and they'll test your understanding of the equation by giving you graphs and be able to show what what a single point in the graph would represent. Now, in your actual exam, you have to do entropy change calculations, and you need to be able to draw or sketch graphs related to a particular type of reaction or its entropy change, and be able to understand it. And maybe even sometimes they may ask for you to give the calculation, and they'll give you the graph, and you've got to use information in the graph to be able to undergo the calculation. I'm just telling you things that you should be aware of when you're going into the exam. I'm not going to go through every single example here. I'm going to just I'll go through a couple calculations. I'll go through some of the graphs. And maybe when I finish physical chemistry, I'll do a video on exam questions on related to free energy. There'll be plenty of them. But for this video, I've got very basic examples because I just want to make sure that you understand the content of this. Now, feasibility. So yeah, I'm going to go straight into this. So free energy is a simple way to determine if a reaction is feasible. Free energy includes both entropy and enthalpy. So feasibility, for a reaction to happen, the total entropy of everything involved must increase. This includes its molar entropies, but also the entropy change of the air when it's heated. Instead of calculating the entropies of everything, we can define the Gibbs free energy change as delta G is equal to delta H minus T delta S. And now that is a major equation that you need to know because that's the equation that it is. Now, as I said multiple times in different videos, if you truly want to understand the topic, you have to do exam questions on it. That's the best way to, that's the only way you can truly say to yourself that you understand truly say to yourself that you understand the topic. Now, you should be able to, you can probably just remember this equation off by heart, but in order to actually, the best way to actually make sure that that you understand this equation off by heart, or like know it secondhand, is by just doing many equations. And if you doing many calculations, i.e. doing many past paper questions, when you do many past paper questions over time, this will come second nature to you, and you will have to think about, I forgot what the equation for Gibbs free energy is. You'll be able to just know it off by heart, as I do for now, and I've already finished my A-levels, but it's a very easy equation to remember. It's called Gibbs free because the name of the guy is called Gibbs, who came up with this equation is called Gibbs. But I want to come back to this point here, right? So for a reaction to happen, the total entropy of everything involved must increase. This includes its molar entropies, but also the entropy change of the air when it's heated. So there's examples for different types of reactions, endothermic and exothermic. So usually we're talking about the particles themselves. increasing in entropy in order for the reaction to happen. But there's some occasions where the compounds are in such a high state of order. Is actually where the particles surrounding that compound, for example, would increase in entropy in order to try and make the reaction happen. So it's not just about there's many factors to entropy, not just the particles themselves, but the particles surrounding those particles. Now that's very complex, and that requires some complex maths, but ultimately it boils down to if delta G is negative, i.e. if delta G is less than or equal to 0, the overall entropy increases and the reaction will happen. The reaction is said to be feasible at this point. So if delta G is negative, the reaction is feasible. And that's because, if you think about it mathematically here, if the reaction is the reaction is feasible if delta G is less than or equal to 0, i.e. negative. Just for the sake of this right now, I'll go to the point less than or equal to 0, but think about negative, right? And that's only possible if, because our equation is, oh, actually, I still need that. So I'm going to highlight that point here. Delta G is negative. Reaction is said to be feasible. Overall entropy increases. Now, if the reaction is feasible, delta G is less than negative, and if that makes sense, right? That the overall entropy increases, because in order for that to be true, it would mean that delta G. It would mean that, sorry, 1 second. It would have to mean that T delta S is greater than delta H. I say T delta S. Temperature is related to, but we already know that there's a link between the entropy and the temperature. As I said in the previous video, go watch that previous video back. I'll leave a link in the description to my video on entropy. But overall, the overall entropy increases because our value for T delta S is greater than our value for delta H. And therefore, if that's the case, delta G will be negative, and therefore the overall entropy would increase because T delta S is greater than delta H, meaning that delta G is negative, hence the overall entropy increases. Hopefully that made sense. All I'm saying here is that in order for this to be negative, it means that the overall entropy must be greater than the enthalpy change. Mathematically, that's just all it is. This value, no. Why does it do that? All I'm saying here is that this has to be bigger than this in order to say that delta G is negative. And that would make sense. So our overall entropy needs to increase anyway for the reaction to be feasible. So here I've got a little graph of a conversion of A to B. Actually, why has it done that? It's just kind of shrunken down for some reason. I find that kind of weird. Yeah, but anyway, forget about the fact that the graph's kind of shrunken down for some random reason. Here I've got a reaction between A plus B to form C plus D. And only at this point here, where delta G is equal to 0. Now, what I mean by, I kind of skipped on it here because I said I was trying to emphasize on the fact that delta G is negative. But technically, the second that delta G is less than or equal to 0, the reaction becomes feasible. The more negative delta G is, the more likely the reaction will happen, or the more feasible the reaction is. So the more negative the value is, the more feasible the reaction is, because the overall entropy is much higher. Therefore, a very high entropy, the more likely the reaction is to happen. As I said before, you have more possibilities for the reaction to happen, right? But technically, the minute delta G is equal to 0, the reaction is feasible, and at that point, we can say the reaction will actually happen. So here, from A to plus B, the reaction isn't feasible for the conversion of A plus B into C plus D. But once delta G is equal to 0, at that point, the reaction becomes feasible, and we can start forming C plus D. 1 second here. As you can tell here, in our equation, there is a temperature dependency. So if a reaction has a negative entropy, i.e. is a exothermic reaction, and has a positive entropy, it will always be feasible. Think about that mathematically. If we're taking away from a negative number, our value will always be negative, i.e. delta G in this case will always be negative, and therefore the reaction is going to be feasible. But some reactions are endothermic or lose entropy. These reactions show temperature dependence of feasibility. I'll explain this what I mean in more detail here below. But if a reaction has a positive, so endothermic reactions, right? So I've got a graph here that I want you to I want you to understand what I'm talking about here. When I'm talking about entropy, feasibility. So if you get this graph, you will understand what this topic is all about. And this I've got one for exothermic reactions as well. It's not just this one here, but this is just the example for endothermic reactions, right? So it's kind of what I was talking about already. So if a reaction has a positive delta H, which is what it would be for an endothermic reaction, it will only be feasible if the delta S term is positive, i.e. the T delta S term is positive and has to be larger than it. Now, technically, the reaction is feasible when T delta S is just equal to delta H, because that would mean that if we look back at our equation where delta G is equal to delta H minus T delta S, if these two are equal, then therefore delta G will be equal to 0, and at that point the reaction is feasible. But if we're talking about it really being the reaction actually happening, as I said before, the more negative your delta G, the more likely the reaction is to happen. So in order for delta G to be negative, it would have to mean that T delta S is greater than, and this is actually a term that they like to use, that they want you to use in your exam when you're answering 3, 4, 5 mark questions related to this topic. Is a 3 or 4. Don't worry about writing a massive essay. It's part of the answer is you sketching the graph or doing some sort of calculation, and then it's like a little statement at the end. But saying this here, that T delta S is greater than or equal than delta H, is more likely just going to be T delta S is greater than delta H. Therefore, delta G is less than 0, and therefore the reaction is feasible. Now, hopefully you understood that basic concept there, right? Now, for delta H here, if this is an endothermic reaction that we're describing, therefore the delta H. Now, this is delta G here, but we all know that this is a delta G, delta H have some sort of proportionality here. The same way that temperature and entropy are proportional to the extent that having a high temperature would mean you'd have a high entropy. So that's why we'd say that T delta S the reaction has a temperature dependency because of the effects that temperature has on entropy. But delta G here would be high because this is an endothermic reaction. Our delta H here is actually high as well. Now, I'm not going to put delta H because it might confuse you, but the reason why it's starting off so high, or delta G is starting off so high, is because it's an endothermic reaction, energy is going in, we're starting off with a very high enthalpy value. But that's not what we're telling you. This is delta G, but I'm just explaining why it's like that, right? As we increase the temperature, right, because delta S, say we have a very low delta S, but a very high delta H. At this point, so from here to here, everything up until to that point, delta H is actually greater than our delta, than our entropy. In general, our delta H is much greater than delta S. Initially, at this point here, right, at x equals 0, I should say at x equals 0, our delta H is way higher than our delta S. But we're forgetting that it's T delta S. T. And that's why temperature has a great effect on, it's very important to understand the effects of temperature on this equation. Because if we increase the temperature, we can then, because delta S alone won't change anything. Delta S is specific for that reaction. But if we increase the temperature, we increase the entropy, as I said before, right? And therefore, between these 2 points here, between everything up until this point, delta H is greater than T delta S at this point here, right? I'll go kind of use my highlighter. At these points here, the delta H is greater than T delta S. But at this point here, right? Yeah, actually, let me remove these arrows here because they're not really necessary here. But at this point here, no. At that point there, T delta S is equal to delta H. And that at that point there, the reaction is feasible. Because for a reaction to be feasible, delta G just needs to equal 0. But at that point there, we see the reaction is feasible because T delta S is equal to delta H and delta G is equal to 0. More importantly, just saying that delta G is equal to 0, therefore the reaction is feasible from that point onwards. And therefore, from this point onwards, actually I want to use from this point onwards, the reaction is now feasible. So I use this. So from anything beyond that temperature, now we can actually measure this temperature, or we can calculate this temperature. Now it's more likely that you're going to calculate that temperature because that's what you're going to do in your exam. So say this we're going to call this temperature X, right? So from temperature X onwards, the way you'd word this in your exam is that for this specific reaction, the reaction becomes feasible at X Kelvin. Though it will be in Kelvin because that's what we use. By the way, I forgot to mention that delta G is in kilojoules per mole because that's energy. Kilojoules per mole or joules per mole. Enthalpy original is kilojoules or joules per mole, and temperatures in Kelvin. Delta S is in entropy is in joules per Kelvin per mole or kilojoules per Kelvin per mole. Should I write that out? No, I'm not gonna say that. Delta G and delta H are the same. Temperature, which is just joules or kilojoules per mole, because they're energy. Temperatures in Kelvin. Delta S is in joules per Kelvin per mole or kilojoules per Kelvin per mole. Yeah. But at this point here, all you're saying here is that when the temperature reaches, so the reaction becomes feasible at X Kelvin, because at this point, delta H is equal to T delta S, or you could just say T delta S is greater than or equal to delta H. Delta G is less than or equal to 0. So I can use this. Delta G is less than or equal to 0, and therefore the reaction is feasible. So that's all you're saying here. So reactions that was for reactions that for an endothermic reaction. Reactions with a negative entropy change. So entropy always increases. So for a reaction to happen, if the standard molar sorry, I kind of lost my words there. Entropy always increases. For a reaction to happen, if the standard molar entropies of the reactants decreases, I can't speak today. My bad. Entropy always increases. For a reaction to happen, if the standard molar entropies of the reactants decreases, it must heat its surroundings and cause the entropy of the surroundings to increase. So the reaction must be exothermic. So this is an example of an exothermic graph. I was going to say what it says above. It's meant to be below. Ignore that. Below is a graph of delta G versus temperature for negative delta H and delta S. So this is what I was just talking about here. Entropy can always increases, right? But for a reaction to happen, if the standard molar entropies of the reactants decreases, so if the entropy of the reactants decreases, it would have to heat the surroundings. And remember, in an exothermic reaction, energy is being released to the surroundings. So that the reactants themselves are losing energy. And if they're losing energy, they're losing that kinetic energy, they're losing also that heat, they're losing entropy with that as well. So, but because they're spreading the heat outwards, the particles surrounding it uh, are gaining that heat or gaining that internal energy, and therefore they're increasing kinetic energy, and therefore they increase in the particles surrounding the particles would increase in entropy. So the reaction must be exothermic, and below here is a graph of delta G versus temperature for negative delta H and delta S. So this is kind of the flip of what I said in the previous statement. Because this is an exothermic reaction, we're starting off with a very low delta G, but it's the same overall principle that the reaction, it's the same overall principle where delta G is feasible if it's less than or equal to 0. But in this case, it's different, it's flipped, where usually we would say that we'd have to increase the temperature to a certain value. With this one here, we had to increase the temperature, and the reaction is only feasible when we increase the temperature to that value. But in an exothermic reaction, the reaction is feasible until, so this, the reaction is actually feasible until we reach a certain temperature. So everything until here, the reaction is feasible because delta G is less than 0. This would be our overall delta G here, or this is the y-axis, and delta G here in general, up until this point here, not this point there, so I should have used the arrow differently there. Up until that point there, the reaction is actually feasible because delta G is less than 0. Once we increase the temperature past this value here, the reaction is no longer feasible because delta G is more than 0. And therefore, that would mean that our entropy is less than our enthalpy, and the reaction is no longer feasible at this point in time. At that point in temperature, I should say, at that temperature. So it's just about understanding what the graphs here mean. Essentially, we're saying if you understand that delta G needs to be negative, the reaction is feasible so long as this delta G here is less than 0, right? So the minute it crosses this border here, we're stepping into a region where the reaction is either feasible or not feasible. And if it's above 0, the reaction is not feasible. The same here. If it's above 0, the reaction isn't feasible. If it's below 0, and I know I've said this many times, you're probably getting annoyed with me saying, I understand what you're saying. I hear your point. I am probably annoying you a lot by me constantly saying it, but that is literally all you need to understand. I'm saying it many times so you understand why I'm saying it, and it's because that's the only thing that's relevant here. That's the only thing that's relevant here, is whether or not delta G is less than or equal to 0, and the only things that are relevant are in the equation. Is delta G less than 0? Okay, and at what temperature does the reaction become, where does it reach that threshold? At what temperature does it reach the threshold where delta G is less than 0? And it's at this value here. Now I'm going to call this one Y, because this is a different reaction, but once the temperature, in this case here, we said that for an endothermic reaction, the reaction becomes feasible once the temperature reaches X Kelvin, and at that point delta G is less than or equal to 0, and therefore T delta S is greater than delta H, and the reaction is feasible. In this case here, the reaction is feasible until you reach temperature Y, because at this point here, if you exceed temperature Y in Kelvin, delta G is T delta S is T delta S it becomes more than, no, T delta S is less than or equal to delta H, or just more than, it's just less than equal to delta H, and therefore the reaction, therefore delta G is positive, and therefore the reaction isn't feasible. And if you ever get confused or if ever muddled up with your words, just think about that equation. Just think about the equation here. If this is bigger than this, then our reaction is going to be, then delta G is going to be, so if delta H is bigger than T delta S, because we're trying to take away T delta S from delta H, the reaction is no longer feasible if delta H is bigger than T delta S. Whereas if T delta S is bigger than delta H, delta G will be negative and the reaction is feasible. It's just basic maths here. All I'm asking you to understand is basic maths and how to answer it. So always saying is, so temperature is less than temperature Y, the reaction is feasible because T delta S is greater than or equal than delta H. Therefore, delta G is less than or equal to 0, and therefore the reaction is feasible. So a couple of free energy calculations. So free energy calculations, you can calculate the temperature at which a reaction becomes feasible. So feasibility. So for a reaction to happen, delta G must be negative. I've already made that very clear already. We can calculate the temperature at which a reaction switches from unfeasible to feasible by setting delta G equal to 0. To find the temperature, we must rearrange the equation that gives free energy. So delta G is equal to delta H minus T delta S. And it's about very, very simple rearranging of your equation. You should be able to do that. As I said before, the reaction becomes feasible when delta G is equal to 0. So if we know that delta G is equal to delta H minus T delta S, so that's a terrible H, that looks like a reverse N. We can assume that delta G is equal to 0. We can leave it at that. We're not assuming. That's what we're trying to theoretically prove. So if delta G is literally equal to 0, so 0 is equal to delta H. I can already see it from here because I've done it many times, but I'm just going to show you step by step. We're trying to just get T. Very simple to see here. Just move T delta S to this side. T delta S is equal to delta H. And if you want to get temperature specifically, because we're trying to work out the specific temperature where the reaction becomes feasible, then T delta S is equal to T. So temperature is equal to delta H over delta S. Now, be very, very careful. Now, this is the arrangement, but the only thing you need to be aware of here is, well, actually, yeah, be very. I want to see if you spot it, actually. I'll go for an example. Yeah, I'll go for an example and see if you make the same mistake that I did the very, very first time I did it. And it's to do with, I'll give you a hint, it's to do with the units. But here's an example from, well, Seneca produced an example of bismuth extraction. So, a step in the extraction of bismuth from its ores is the reduction of bismuth hydroxide, which is BiOH3, by hydrogen according to the equation. 2BiOH3 plus 3H2 goes to form 2Bi plus 6H2O. If the entropy change is plus 400 joules per Kelvin per mole, and the enthalpy change is 50 kilojoules per mole, what temperature does it become feasible at? Now I want you to try and work this out and explain in the solution at the end. So I want you to pause the video now and try and answer this question here. Or technically this question here. Try and work this out. I'm going to assume you've tried to work out the temperature at which it becomes feasible. If you haven't, then that's just do that now. But I'm going to show you how to do it. So first of all, in the exam, if you ever just slightly forget, delta G equals to T delta S. Sometimes it's actually, sorry, not T delta S. Sometimes it's actually useful just writing down this equation. Sometimes they may want you to show this equation at some point. Or even if you're not doing an equation, just showing that you're trying to convert to this equation. Even though it may be very simple, just showing that you can rearrange this equation can do you want this? And you have to do too much in depth. Just show delta G is equal to 0. 0 is equal to delta H minus, I know I'm kind of going through it pretty quickly here, but you guys can see what I'm going on here. So T is equal to delta H minus, so T is equal to delta H over delta S. Now, temperature is equal to, our delta H is, now be careful here, it's not 50, our value is 50,000. Unless you're going to change the entropy into kilojoules per Kelvin per mole, which you could do. There's nothing wrong with it, unless they specifically say they want it in kilojoules per Kelvin kilojoules per mole. Then you have to convert the 400 into kilojoules per Kelvin per mole. But if they want it in the value just to be in, actually we're doing temperature, so either way it shouldn't matter if you're doing it in kilojoules per mole or joules per mole. You're working at temperature, which is going to be in Kelvin. All you need to make sure is that you're using the exact same units here in terms of kilos. This is 400 joules per Kelvin per mole, and this is 50 kilojoules per kilojoules per mole. So it would be 50,000. It's 50,000, not 50. 50,000 over 400, or you could do 50,000, or you could do 50 over 0.4. Up to you. I would prefer doing it this way because it's pretty easy to cancel it out, but it honestly doesn't make a difference because you're using a calculator anyway. Cancel this out. I can just see from here 500 over 4, that's 125. The temperature is equal to 125 Kelvin. And that's it. And all is, if this is a so we've worked out at this point the reaction becomes feasible. We said this is a endothermic reaction. This is an endothermic reaction. Yeah, if this is extraction of an ore, you need to put energy in. You need to put energy in to actually extract the ore. So it would make sense that this is an endothermic reaction. And even says with the temperature which it becomes feasible at. So at 125 Kelvin, the reaction for the extraction of bismuth becomes feasible. Anything less than this temperature and the reaction isn't feasible. And that's it. That is all I have to say in this video. I know it's probably a bit long-winded, but that is all it is. Thank you for watching, and that is